All right. So I think on the previous page we discussed a scenario where we can the prover, dishonest prover, can cheat without even knowing the yes, and that happens, only for half of the time. And then over here we are going to discuss that can happen only for 50% of the time, but not more than that. So let me expand the idea. Probably I'm gonna need another page. Let me just add it now. Page 17. All right. Okay, so let's look into the computation tree. So essentially what we have is we have a prover and then we have a verifier. So the communication is like prover would send A, verifier would respond with a C, and then the prover answer or respond back with B at the end. So this is the computational tree. So we have a dishonest prover, and then this honest prover would, we are trying to see all possible scenarios over here. So let me draw this one. So when we are talking about the dishonest prover, we said that we compute A1. So when we are talking about A1, he would respond with this probability of 1. And then so we get to the verifier. Verifier would either send us a C equals to 0, or he would respond with C equals to 1, the challenge. And then these are assumed happen with the probability of a half. And then the prover would respond with two of these cases, right? With the B1 that assumed that with the case that we assumed that the challenge was 0. Oops. This is actually or C prime, and or we respond with B1 of 1. This means that we assume that or guess what was C to be 1. And then and you can see that only in one of them we can succeed, and in other one we would basically fail. So let's recap again. So the prover, the cheating prover, would choose on a C prime. He guessed that maybe the challenge would be 0, for example, and then he will compute he will randomly choose a B, and then he would choose. Let me write them down here. So we start with the C prime I to be 0 or 1, and then we compute BI for this randomly. We would guess the BI for this bit that we just guessed to be like that, to be we let this to be from ZP minus 1. We randomly choose this one, and then we compute AI to be G to the power B I C I prime divided by X to the power C prime, right? So we guess the CI, we guess what we would send us, the challenge either 0 or 1, and suppose we guess to be 0, and then we can compute, we can choose BI, and then we can compute A, so we respond with A, and then we wait over here. We would send us 0 by probability of 50% or 1 with the probability of 50%. In this case, we would fail because we guessed that the challenge was 0, but we receive a challenge to be 1, so we failed. We can return this one. We just abort. or maybe we just return some random value, but of course we would abort, or we would fail with a very high probability. And then over here, when the challenge is 0, we already guessed that this is 0, so we crafted A so that we can pass that equality, so we would basically succeed if that is the case. Following with this computational tree, so at other point he can send A2 with probability of P2, and then the verifier would send again C equals to 0 or C equals to 1. And then if we follow this computational tree, so over here we would have B2 of 0 or B2 of 1. And then again, one of them we would succeed, and then the other one we would fail. So if you see every branch, there would be one that would fail and one would basically succeed. And then let's say that this is the AN, the last one that we can choose with the probability of N, where the sum of this probability of i's become to 1. So we get to this verifier, and then the verifier could choose basically between C equals to 0 or C equals to 1. And then for either of those cases, we would respond with the corresponding, Bn now, 0 or Bn 1. And then maybe this one would fail and maybe this one would succeed, right? Depending on what we've guessed. And then, so this is the entire, with the different probabilities that this AI are chosen, but now we have the computational tree. These are the entire value of A's that you could choose. AN is a value from Zn. So, these are all possible things that imagine that can happen. So when you come over here and you count, you see that the number of the successes equals to the number of failures, right? Which means that P star can cheat. Wow, what a star happened to be there. P star can cheat with only the probability to become 50%, right? So no more than that, because if you look into these branches, we can only guess one of CI to be 0 or 1, and we can only answer for the case that we guess the challenge correctly. And if you see this computational tree, then this is what we expect to see. However, let me go to the next page. However, what happens if somebody claims that they can cheat with probability more than 50%? So let me show you here. If the probability of P star to succeed is more than 50%, then that means that looking into the above, computational tree, there exists a branch with 2 success, right? So if I go back over here, so we know that after we do all this computation, we are supposed to have equal number of success and fail. And if somebody claims that they can win with more than 50% probability, that can only happen if there is a branch over here that in that branch we have 2 succeed, right? So that means that probability, the number of S is getting greater than number of failures. And so I suppose that this could be that branch. So let's say that is the branch I. So the P star would reply it AI, and then the verifier would send either C equals to 0 or C equals to 1, and then the prover, the dishonest prover, would reply with bi for 0, and then or bi for 1, and that means that he can basically he can succeed with both of them. So no matter what challenge you send and receive, he will succeed. So remember that we started with the dishonest prover because this dishonest prover doesn't know the secret S, right? If he knew the secret S, of course, just like a normal prover, he would be able to compute the B. But we started with the P star or dishonest prover because he doesn't know the S. So he can succeed with both of this. So this would become very interesting, so that even though he doesn't know the secret S, now it looked like that he can win in in both cases. So if this is the case and there is such a branch, and that would be the only way based on our computational tree that the probability of success becomes more than 50%, let's just recall that X was G to the S mod P. So when he wins for both cases, then we should have these two equalities. So G to the power BI when the challenge was 0 equals to, is congruent to X to the power C0 AI mod P. And then also we have G to the BI of 1 is congruent to X to the C1 AI mod P, right? He can basically come up with the BIs that he can satisfy this both equations. Then if we divide these two equations, right, so we would get G to the power BI 0 minus BI 1, right, equals to X to the power C0 minus C1. And then AI are the same, so they just get canceled, mod P1, mod P. And looking into this equation, we know that X is nothing but G to the S. So then I can say that G to the power BI of 0 minus BI of 1 is equal to G to the S, right? Because X was G to the S of C0 minus C1, right? Mod P. And then from here, P is known, G is known, BIs we know, and CIs we know. So the only unknown on this equation is S. So that means that S equals to BI of 0 minus BI of 1 divided by C0 minus C1 mod P. And that means that that implies that P star knows or secret S, which is a contradiction because we said that we have a cheating prover, that this cheating prover doesn't know our secret S, right? And he can only cheat for half of the time, and it is only can work when he guesses the challenge correctly. But when somebody claims, some prover claims that this prover can cheat for more than 50%, then this, according to our computational tree, this is the only way that that can happen, that there is a branch that he can succeed with both challenges. And if that happens, we see that based on our computation, we can plug in, and then we can see that we can basically, based on this information, we can compute S, which is the secret key, and that means that the cheating prover knows the S. That is the only way that this can happen, and therefore that contradicts because we assume that our cheating prover doesn't know the secret S, and he can win for only half of the time. So therefore this cannot happen, and the prover cannot cheat, can only cheat for exactly 50% of the time, and it cannot be more than that. So this completes our proof. Going back to the protocol itself, so that was what we discussed. And then we are going to talk about the case number 2 now. So there is it is very interesting material on the case number 2, and it says that if we run this, what if we want to increase the likelihood that we detect this sort of cheater? Because even though we run on a normal protocol, we know that some cheater prover can win with probability more than 50% of the time. So what does that mean? So let's look into this. Let me give you the index. So we are talking about this prover that works with this verifier. We said that it would send A1, and then we would receive a challenge C1, and then we respond with something like B1, right? And then the probability of the P star to cheat and succeed is exactly 1/2, right? And then this is like the first run. For the second run, we can also do the same thing. So we run the protocol T times, right? And then the same thing applies, right? Again, that it would win is exactly the same amount. And then we continue this for T times. So we run this very same protocol for T times 1 by 1. And again, remember that if in any of these steps the prover abroads or the answer that is sent doesn't get verified, then the verifier would stop in any of these intermediate steps and says that, well, I catch you, you are not an actual prover. And so far, whatever you have sent to me, it happened to be correct because you were cheating, but you fail on this, whatever interaction somewhere from 1 to T, and then you lost then, right? So the probabilities for any of these individual ones are the same. But when we run for T times, then the probability for the cheating prover to actually be able to cheat, it would become 1/2 to the power T, right? So it would go down exponentially. So let's say you run it once and there is a 50 chance that he can the prover is not, for example, Alice that wants to log into Gmail. And if you just run it once and there is a 50% chance that, Eve can log in instead of Alice. But if you run it twice, then that probability would become only 25%. And if you run it 3 times, that probability would become 12.5%. And if you run it again for the 4th time, that probability would become 6 something percent, and so on and so forth. That goes down, and more and more. So the idea is that if we run it for T times, where you get convinced that T is this entire probability would become small enough, then you can run this entire protocol for that many times so that you get convinced that this prover is not able to cheat. So you are able to catch him in one of these rounds. And if you don't catch it, after too many rounds, then that prover must have got very lucky. But the point is, the truth is, we increase this T, we let this T to be large enough so that likelihood is basically very small. Right. So if I want to recap so far, we have come to see a new system where we can basically do identify somebody by not sending the secret information, but rather than that, we use the secret information to do some computation, right? And that computation would help us to judge whether this prover is the person who claims to be or not, right? And then the beautiful thing about the system is, again, that we just use that secret information to do the computation. We never share like username and password. We never share the secret S. We just use it for the computation to prove. So far everything looks okay. So we have some mechanism we look like that we can catch this sort of prover, or let me say dishonest prover. But another thing that is very interesting to discuss is that, so suppose the prover is not a dishonest prover. Prover is Alice. And then the next question that we want to ask is that, well, so okay, this is really Alice and she used her secret information to do that calculation. But the next question that can come across your mind is that, can verifier learn anything from that secret key, secret S, by just interacting with the prover? So we know that prover uses that S to compute B and answer the last line. But now the question is that, suppose that we use this interaction, we engage into interaction with a real prover for many times, right? Let's say for a year worth of everyday communication. Would we able to verifier would be able to gather this all communication that he had with prover, and that communication helps the verifier to learn something about that secret S or not? So that is going to be our discussion for now. And then we are going to talk about now V prime, or sometimes I also call it V star, and that is going to be our dishonest verifier, right? It would be very interesting. Now we show that prover can cheat sometimes, but if we run it many times, we can catch him. So we have ensured the verifier that this scheme could work. But right now we also need to convince the prover that if you engage with this kind of verifiers, you don't leak any information, and that would be very interesting thing to see. So I'm going to expand over here before we go and see any of this construction. So we kind of get a bit more idea of what is going on with this claim that we are making here. So we say that the question that we want to answer is that, can V star, the dishonest verifier, cheat to get information about the secret S, where remember that X equals to G to the S mod P, and we are talking about this X, this S. Okay, so this is the question that we want to answer. So going back to our scheme, we see that we have a prover, and also we have, let's say, we have a cheating verifier. So prover would send some value A, and all verifier does is sending a challenge C from 0 and 1, right? So the question is that over here, how can V star cheat? By cheat we means get info by sending this C from this challenge from 0 and 1, right? So that is another way to ask the same question. So in order to answer this question, so I would like to talk about something called transcripts. So P and V would, in an ideal world, they would start to send messages back and forth. So no matter what kind of a scheme we design, just now we are talking about this discrete log, but there are other ways to design, different ones. So ideally, what we want to see is they are sending and receiving messages. So prover would always start with M1, the verifier would respond with M2, and then the prover would say M3, and then maybe it is the same protocol that we would run it many times, right? And then so on and so forth. So this would continue until, M times. So n different messages has been sent and received, right? So now what we are saying is that the verifier, the dishonest verifier, computes knowledge from M1, M2, M3, all the way to M, right? So he collects these interactions, all the things that he sends or receives from this interaction. So, okay, so that is the point. And then we are going to show from now on. So, you know that every step we start with a big question, and then we are trying to break it down to the pieces and based on the information we get. So now what we are trying to show that, so we are saying that, so verifier, if he's gaining some information, or he should be getting them from this interaction that they can have right here, right? So now I would reframe the question to say that how can we show that the V star can't get any info from M1, M2, all the way to MN. Okay, so that is the question. So this is the question that we want to answer. If we can show that he cannot gain any information, then we are fine. Then we are done with what we were trying to do. So here is the idea. Let me change the color so that we start to see that we are getting to the answer. Short answer. Use simulator. Okay. Let me see, how much time do we have? Okay, we have some good amount of time for this discussion. Let me also plug my laptop. Looks like that it's going to die soon. All right. So we are going to play with two words. So let me expand to see how things were working so far. So we were working with some prover that has some secret information S, and then this guy interacts with some dishonest verifier where X equals to G to the S mod P, and this notation means that P knows S, right? And both of these guys, they have access to some random source. They use this random source to, we would use that one to, get the challenges, and prover would use that random source to, randomly select, R, or randomly select B, and so on and so forth. So both of them, they have access to the random sources. And when you look at their interaction, then you see that they are interacting, and some messages M1, M2, all the way to MN is coming out. Okay. And so we are going to use, as I said, the idea of a simulator. So how that can help. So suppose now that I have my verifier, the same verifier, but I don't have a prover. I want to simulate the existence of a prover. So again, I know that x equals to g to the s mod p. And then I'm going to use the idea of a simulator. And then the simulator S that does not know the S for our password or secret, does not know secret S, right? So I'm gonna, in one word, imagine we have two different words. In one word, I have the verifier, the same verifier that is interacting with the true prover that knows the S, and then, you know, out of their interaction, M1 to Mn get out. In another word, I would replace that prover with some simulator, and then the simulator doesn't know the secret S, but I would allow them to interact, and out of that interaction, some messages M1 prime, M2 prime, all the way to Mn prime would get out. If I do this simulation carefully, and these two words are identically distributed, then so let me pause here and see what does that mean. So imagine you're the verifier, and then some of your user would contact you to, you know, to access your services, and then you would say that, okay, if you're a prover, prove that you are the one that I should, you know, you're my user. And we play in two words. In the first word over here on the left hand side, you see that you're interacting with the actual prover that has the secret S, and of course, you know, it would convince you that he's a prover based on the scheme that we designed. And out of that convincing thing, you see that this interaction, the messages that the verifier would see. And imagine, in another word, you're not interacting with any prover. It is just a simulator, but this simulator is somehow able to give you the transcriptions, the same sort of messages that you would see with the actual prover. And at the end, you get convinced that this is also a prover because he's answering the challenges correctly. So if now what we are saying is that if this verifier cannot tell which word is he in, like he's interacting with the actual prover or he's interacting with the simulator. If he cannot tell that, then there is no way for him to gain any information by interacting with prover. Because if he claims that he can gain information from this interaction from M1 to Mn, then he should also gain from information from this M1 prime to Mn prime. You know, because he cannot tell he's playing with the prover or with the simulator. And then if he does that claim, then you will say that, well, I let you to play with the simulator, and then you say that you gain information. But the truth is the simulator itself doesn't know that secret S. So how could you get that S, right? Unless if you are breaking some hard assumption, then there is no way for you should be there to be able to tell me that you know that secret S. So over here we say that no info can be obtained after interacting with simulator. That simulator without knowing S. Secret S, right? The simulator itself doesn't know the doesn't know the secret S, and then we are kind of letting the verifier to interact with our simulator, and then he claims that he knows, he learned the S, which would be impossible because the person who was interacting with you didn't know the secret S in the first place. So if you're gaining any information, it means that you are breaking some hard assumption. For example, you're breaking, discrete log hard assumption, but which we know that it is not possible. So the only thing that we have to do is that verifier, we should make a simulator and show that verifier cannot tell if he's interacting with the actual prover or he's interacting with a simulator. If he cannot tell these two apart, then the rest of the things, the logic is here. If these two words are identical, he cannot tell which one is he playing with. We can always let him to play with the simulator, and we know that our simulator doesn't know the secret key. So even though they interact for infinite amount of time, then they wouldn't be able to, the verifier wouldn't be able to learn anything because the simulator itself doesn't know the secret S. It's just like producing this accepting messages to the eye of the verifier. Right. I think we would get to some examples, and this would become very much understandable by the time that we would start to give you some examples. So what we are trying to do is that we want to prove that the scheme that we design is a zero knowledge. So zero knowledge also means that, the same thing. The cheating verifier cannot learn anything. And the scheme that achieve that, we call it the zero knowledge proof system, interactive proof system. So what we are saying is that no knowledge is transferred from P to the verifier by interaction, right? So imagine again the interaction. So we have prover, we have the verifier. You send A, he sends C, and then he interacted with B, right? But we are going to have some restrictions over here. So the prover and verifier are the parties that are in this algorithm. Now we are going to design a simulator, so we need to be careful about some of the notations. And then we assume that they are probabilistic polynomial time Turing machines. So the Turing machine is a model of our current PCs and servers. They are all a kind of Turing machine, and they are a polynomial time algorithm. So we cannot run exponential time algorithm. That now on the common input message, which is our public key, this is equal to G to the S mod P. We can see that some messages going from P to V, and then some responses we are getting back from V to P. And then after that they have done their interaction, so we would want to say that the transcripts between the prover and verifier, which is their joint computation, you are going to represent it by this one. The transcript between the prover and the verifier on X, which is our public key, is M1 to Mn. And this you can imagine that it would be a set of only accepting transcripts, right? So we only collect those transcripts that are accepting at the end, because those that they fail, it doesn't have any value for us. Those would basically the verifier would abort at the end, so wouldn't be valuable for the verifier. So at the end, we are looking into some transcripts between the prover and then the verifier on our input X, which is going to be a set of something like this, A, and then they send a C, and then we compute a B such that G to the B equals to A times X to the C mod P. So we have a set of these three tuples, right? A, C, and B. And then we only are interested on those that are accepting. That means that they pass this condition over here. So we would keep collecting such a set. So we're just trying to be a bit more formal, like how we would handle the information. So remember that this transcript itself, like M1 to MN, all those values are a random variable because, well, if you look at the computation, you choose a R and then you set A equals to G to the R. So A is a random variable because it comes from some randomness R that we have chosen before. So this all values look like some random value. And then where this randomness come from in the first place, it comes from those random bits that we gave the P has or V has. P would choose those random bits to choose R. V would choose those random bits to choose challenge C, and so on and so forth. So that is like they have their own random sources. So here is our formal definition. We say that a prover and a verifier is a perfectly zero knowledge proof. Okay, if there is an expected probabilistic polynomial time simulator that for every, probabilistic polynomial time verifier and for every input x, the following two distributions are identical. We want to have this S that, this on input, he would be able to generate the transcripts. And okay, let me put it this way. When we interact with S on input X, that here we don't know the S, the secret S. And then we collect those transcripts. And also we also collect the transcripts that where verifier interacts directly with the real prover that knows the secret key S. And this is the transcripts. And then we hope that these two things, they are identical. Their probability distribution is identical. So if prover is verifier, this honest verifier is, if these two are not identical, then the verifier can tell if he's playing with the real prover or he's playing with the simulator. And if that happened, our idea of using simulator wouldn't work. So we need to somehow make sure that the output of our simulator is the same, in another word, simpler word, is the same as the output of our prover, so that no statistical test can also tell that apart. So if that is the way that our verifier distinguishes between these two words. But we would get back to this one very soon. So something that is interesting for you over here, that you see that we always keep saying that simulator has to be polynomial time Turing machine, and the verifier is a polynomial time Turing machine. So the simulator, imagine the word that instead of the prover and the verifier, which is the simulator, imagine that I designed this game. You talk to a robot, or nowadays you talk to Alexa, and also you talk to a real person. If for example, your friend has a secret information in her brain, and then you want to get that secret information, but imagine that we design an Alexa that has exactly the same accent as your friend, and then you can tell you're talking to Alexa or you're talking to your friend. If their accent and the voice, the nuance, everything are equal. So if you can't tell if you're directly talking to your friend, maybe make a phone call, and then you need to tell if this is your real friend or this is Alexa that is talking for your friend. And then at the end of this conversation, you would tell, I got that secret information out of my friend's brain. And then we are saying that, no, you didn't talk even to your friend. You were talking to computer. You were talking to Alexa. And Alexa didn't know that secret information anyways. So then you're lying, because the information that you got is what you claim is not true, because Alexa didn't know that secret information about your friend. She just had the same voice as your friend. So in doing that simulation, so that is the whole idea. In doing that simulation, we need to make sure that the Alexa algorithm runs in a polynomial time. Because suppose you ask a question, your friend would answer right away. But if Alexa is not a polynomial time algorithm, you ask a question, then I don't know, 10 minutes later, Alexa would come back with the answer. Even though the accent is the same, then you say that no, that is the computer. Because if I talk to a human, it wouldn't be much of delay between our communication, right? So that delay would be one of the issues because the verifier can distinguish and tell that no, I was talking to a simulator simulator because that took a long time to get the response. Right. So so at the end, by telling you all these stories, we are trying to say that in a zero knowledge, proof of system, if some system is a zero knowledge, we have this security property that no verifier, regardless of it is honest or dishonest, can gain an information from the prover by interaction. So that is the number one. And then the reasoning for that is that, as we discussed, I think just like with some words, I think that would be very interesting for you to have it. So if you can get information from the simulator, it means that, the simulator should have that secret knowledge S, which it doesn't. So I think this AI example, I hope that it really makes it clear for you guys to understand how this idea would work. I think next week we would start to give more examples about this zero knowledge proof. Now, I think we would have a couple of examples to discuss. Some of them are zero knowledge proof and some of them are not. So then you will understand that how to check if some proof of system is a secure one, is a zero knowledge one, and some of them doesn't have this property of zero knowledge proof. All right, maybe I would just stop here. Let's see if there are any questions.